And let's spend the few minutes we have left setting up a bias of our law problem that we'll finish solving next time. Well, we can solve it. That's okay. Okay, I have here a wire, which is mostly straight, but I've bent part of it into a semicircle of radius r. And this wire carries a steady current. I would like to know the field, the magnetic field due to the wire at this point, right at the center of the semicircle. Alright, so it looks to me like I'm going to have to integrate 3 times, right? Anytime I have this sort of kink in the wire, really anytime a wire is going to change shape, that's going to represent a discontinuity in something, right? If this were a graph, it would be a discontinuity in the first derivative, but it's not a graph, but it's going to represent a discontinuity somewhere. So my standard way to handle that is going to be piecemeal integration. I'm going to calculate the field due to this wire, add it to the field due to this wire, and add it to the field due to this wire. Okay? So in general, when I see this, B is going to be integral over section 1 plus integral over section 2 plus integral over section 3. And that's the general way that I would handle that, where we'll call this 1, we'll call this 2, we'll call this 3. I'm okay adding up the integrals because integration is just addition to begin with. Okay, so let's see what we can do. In this particular case, we can simplify this. You might see what the field contribution from section 1 at that point is going to be. Think about it. What would you want it to be? You would want it to be 0, right? Well, is it going to be? Okay, here is your current vector I dx I hat, right? Dx I hat is going to be the path of integration. All right, remember, maybe I should write down the path of our mu naught over 4 pi integral I dl cross r hat over r squared. Okay, remember what these vectors are. dl is your path. R hat points from your differential path element to your observation point. Your observation point is right here. dx I hat is right here. Where is r hat on that diagram? It's right here. Right? Points from your differential element to your point of observation. Right? What is the cross product of these two vectors? 0. Right? Collinear vectors have a 0 cross product. It's because of the definition. Sine of theta. What is theta between those two vectors? 0. What is the sine of 0? 0. So your wishes are fulfilled. The cross product, or I should say the field contribution from this wire is exactly 0. What about from this wire?
0.
Because the angle between those two is what? Pi 180. Yeah. Here is your dx I hat. Here is your r hat. Right? From the source to the observation point. So, and that's, I should say, this is artificially easy, right? Because there's no guarantee that somebody's going to ask you for the point here. It might ask you for the point here, and that is definitely not 0. There's a non-zero contribution from each of these. But for this point, they just go away, so it's actually nicer than we think it is. So if I'm going to add these up, this gives me 0, and this gives me 0. So I'm only left with the second section. All right, let's do the geometry there. Here is my path vector. This is my differential path vector, VL. Here is our hat, right? Okay, we've done enough cylindrical geometry so you can probably see where we're going to go here. What's my path going to be? So DL is my placeholder. When I actually integrate, how do I turn DL into something over which I can integrate? What is your instinct? What's my integration variable going to be? Theta. I have to integrate over a circle, right? Same thing I did with electricity. So my integration variable, I want to turn this into theta. I do it the same way I did, right? R d theta, that's my length. But I've got to make this a vector. And the x-axis, I just slapped an I hat on it. And the y-axis, I slapped a j hat. But I don't have that. I have this cylindrical thing. So I'm probably going to pick out theta hat. Where theta hat is a unit vector pointing tangentially to that circle at every position. Okay? All right. Let's write down by parts. I got 2 minutes. We can do it. No, we get out at 12:45. It's been like a week since class. Okay, I've got plenty of time. Perfect. All right. No one was going to correct me on that one. No. All right. So looking for the magnetic field, it's going to be mu naught over 4 pi integral. We'll talk about the limits in a second. Well, first of all, I've told you that the current is steady. Can I just go ahead and pull it out of the integral? Mu naught I. And then I'm replacing DL with this guy. R d theta, theta hat, cross R hat over R squared. Okay. So let's take care of what we can take care of. Do we agree that as long as we're going around that circle, R is a constant? See the definition of circle for details, right? That's what a circle is. A collection of points equidistant from one point. It's the radius of the circle. All right, so I'm going to lose this guy. And this can come out of the integral because that's constant. So I'll just do a little blackboard on the front. There we go. Okay. So d theta is going to be my integration variable. What are going to be my limits? That might work. That's not how I would choose to do it. I would go from pi to 0. I'm trying to think what would actually get you. I mean, obviously 0 to pi is going to work, but I think you're going to pick up an extraneous negative sign. And there would be a way to deal with that. It's not obvious to me right now. So let's just do my limits. Pi to 0 is what I'm thinking, right? I'm always going to reference this as my 0 point, right? So if I'm standing here at the center, which is my observation point, and I know that my 0 axis is here, this is pi, and I'm going to integrate it over to 0. 0 to pi will work just fine, but I'd rather do what I'm used to. I have to think about that for a second. So we're going to go from pi to 0. But your instinct is right. It's not wrong, it's just different than what I would. Okay. Now, let's deal with the cross product. My strategy is always going to be is to deal with the cross product before I integrate. Because I really don't want to integrate a cross product. It's just nasty, if it's even possible. It always is. So let's deal with the cross product. Theta hat cross R hat cross product works. Fingers in the first vector, curl them towards the second. So in this position, I have my fingers here, I curl them towards the second, I stick out my thumb, I get a vector that's into the board. So I'll just indicate that to myself here. That's going to be into the board. Right. Now that's only in one position. So the problem here is that neither theta hat nor r hat are constant vectors. They're constant in magnitude, but because theta hat points tangentially to the circle, it's always changing as I go around the circle. R hat is always changing in direction as I go around the circle. So I can't, as it stands, pull either of those out of the integral because they're not constant. And integrating those is not fun. Possible, but not fun. But look at what happens when I actually form their cross product. In this position, I get a vector that's going into the board. I'd probably call that k hat. Right? Well, what if I got a different position? What about this one, right? There it is. Theta hat, and here is r hat. What do I get then? Theta hat, r hat. Well, I get a vector into the board. This is what makes this nice, geometrically. Any position you pick, because theta hat and r hat are always perpendicular, right? Tangent line and radial line, by definition, are perpendicular. I always get a vector into the board. Let's just call that k hat. So this gives me k hat, which we've already seen is actually a constant vector. That's lovely. We're in cylindrical symmetry, right? In cylindrical symmetry, the radial vector is non-constant. The theta hat, the azimuthal vector, which we're calling theta hat, is non-constant. But the vertical axis is constant, just in the z direction. In spherical symmetry, nothing's constant. But in cylindrical symmetry, the vertical axis, or in this case, the into the board, out of the board axis, is constant. That's nice. K hat is the constant. That can come out of the vector, the integral. So what I end up being left with is mu naught I over 4 pi r k hat integral pi to 0 of d theta. And I think you can all do that one. What am I going to get? What's the integral of d theta? Theta. Evaluated the limits. What do I get? Pi. Right? Okay. Does that make some sense? Yeah. There's a negative sign creeping in it. Yeah, it would be -5. Yeah, there. Thank you. How are we going to interpret that? What does that mean? We're going to interpret that by saying that means it's going into the board and that's negative, right? Do I care? Not really. Oh, okay, let me say it. Do I care if it's negative or not? No, I do not. Do I care if you know that it's going into the board? Yes, I do. Okay. The strategy with the vector stuff is always the same for me and for most of you. From the very first stuff in 1600. Throw away the negative signs and just look at it, right? The coordinate system is always yours to control, right? So take an absolute value. If you decide that into the board is negative, you can leave the negative. If you decide that into the board is positive, change it, right? This is going to get you a magnitude, which is what I care about. And the direction is given by the right-hand rule. It comes out of the calculus as long as you adhere to the standard counterclockwise is positive stuff. But I don't care about any of that. I care about you knowing that it's into the board, and then if you call that positive or negative, that's fine. But the reason I don't care is because if you go on the other side of the board, it's backwards, right? So I don't care. As long as you know that it's going that way, that's what I care about. And thanks for catching that mistake. Any other questions here? This seems like a really bare of a problem, but it's not so bad, right? Integrating around circles is much easier than integrating over lines. Any questions? All right, I dare say that's enough after 5 days of no physics, right? And just looking at a week, I shouldn't say no physics. A week before lecture, right? Don't go a week without looking at this stuff. Number one, you're going to have homework. Number two, it's a really bad strategy. So if you have finals,